All right, day 3, here we are. So I'm going to go ahead and talk over the solution we'll present for the homework problem from last night. Josh wanted to point out that this is, of course, only one way of solving this problem. And the whole point behind this type of homework problem was we wanted to get you guys trying some scientific techniques in a context that you understand. We could have presented a very similar Monte Carlo modeling problem using astronomy data, but then those of you who aren't comfortable using astronomy data would have had to learn all the background behind that, et cetera, et cetera, et cetera. So we wanted to give you a problem where we didn't lay out all of the information you needed, but it was in a context and situation where you could figure it out yourself for the context information you needed to solve the problem. So that's why we set it up as sort of a coin jar instead of something that seemed like a real science problem, because we wanted to facilitate the methods as soon as we could without requiring you to learn all the background and nitty-gritty behind the actual science. So we hope that this is a practice that gets you comfortable with some of the techniques of using this object-oriented language. All right, so I'm not going to reread the problem. I'll go over it real quickly, but hopefully you guys looked at the homework. Of course, you make a number of purchases each day. Each purchase has a random chance of costing some dollar amount. And we want to collect statistics over how a coin jar where you dump the remainder from each transaction into, how that changes and accumulates change over a period of time. So we asked you guys to solve this problem using a coin jar. Let's see if I can get this centered better. A class we would call coin jar. So this is the solution that will be up online, or I think actually already is. And what we have here is a much more general object than you probably really need to solve just this homework problem. But hopefully it'll be illustrated when we go through some of it. We have our class here we just started. We have the init function, which you see comes with a double underscore like all of these special functions will. And we have a bunch of default variables up here we've defined, which we'll go over more down below. And here, all our init function does is assigns, self variables to these default variables up here, or whatever you choose them to be. Most of these aren't important right now. We'll come back to a few of them when they get important. So we have the init function as part of our class. Then we have a set of functions that actually solve our problems for us. So this function here models a set of transactions. So let's go into this one and sort of explore what the actual functions we make this work, the actual functions we use to pull this off look like. So here's one of the problems that you have to solve when doing this homework problem, is how do you determine the best change to return when making a transaction? So I would really advise when you build a class like this or build a solution like this, you divide each problem up into its own separate function so that you can call them separately and have a clear hierarchy inside the class itself, so that when you actually use it, it's as easy as possible to use, but you can also go in and modify only the specific functions that perform tasks. So I'm not sure if what I just said was totally clear. It's a little early, I apologize. But basically, I think the way this one was written, in which we have separate functions to perform each task, then functions call functions, etc., it's one of the best ways to build an object like this. So here, this algorithm is probably not the most efficient way to do it, but it definitely handles the job. And one of the points that I like about Python is, for a lot of the problems you solve in Python, you don't have to figure out the most efficient way to do it, because though it does come up, of course, in scientific research where computing power is the limiting factor to solving a problem, most of the time I think it's the biggest waste of time trying to solve a problem is you figuring out how to solve it, right? So if you figure out one way to do it, it'll take the computer maybe 2 seconds longer than the most efficient possible way, but that's 2 seconds. It'll take you half an hour to figure out the most efficient possible way. Anyways, enough about that. This literally searches through all possible combinations of paying for an amount of change and chooses the best one. So I remember when I first solved this problem, I spent a lot of time thinking about the best way to solve this. And I kind of like this algorithm better than what I had come up with. Okay, so now here we have a function that calls both this best change and several other functions to perform 1 day's worth of transactions. And here's another internal function similar to the one above. Okay, and another thing I wanted to go over for this solution is that we have sort of 2 different classes of functions inside this class. We have these functions that start off just with a letter, right? So it's called best change here. And there's an unofficial or maybe semi-official standard in Python where internal functions that are designed to just be used by the class itself, used internally in the code, are prefixed by an underscore. And functions that are designed to be accessible to outside users, etc., are not. So in other languages, you can have strict hierarchies where something like one of these private functions would not actually be visible to someone who just started a cookie class or cookie jar class. In Python, that's not true. If I start a cookie jar, an IPython terminal, and push cookie jar dot, I'll be able to see these underscore functions. So they're still accessible in Python. It's just a convention to sort of keep it in your mind when a function is designed to be used internally versus designed to be accessed outside. Does that make sense? Great. Sorry if I'm a little incoherent this morning. This is earlier than astronomers usually work.
So that's for just a convention for starting with an underscore. How about the ones that start with 2 underscores? Is that just a convention, or is that actually hard?
Well, those are the special functions, and I'm not sure. Does an interpreter treat those?
I believe those are reserved. So you can do whatever you want with that function, str, the underscore, str, double underscore. But if somebody says print the instance of this, that will get invoked so that whatever's printing out will say, what do I need to print? You can use that without having to invoke print or str parentheses for the variable. So you can make new double underscore strs with double underscore, this is my printing method, and you can use them as much as you want, but they won't within the standard Python interpreter get invoked from some other action. Remember, we had the underscore underscore add, the underscore underscore multiply. That's a special thing so that when it sees two versions of the same type of object and you have a plus in between it knows to basically call this adder, right?
So for example, the double underscore str, that sort of represents the string representation of this object. So like Josh said, if you say print this object, the function of this double underscore str is what will be returned as a string.
Is that a part of the attribute as well? The fact that it starts with the underscore is still visible from the outside?
Well, what we saw yesterday, you essentially can't hide anything from the outside.
Oh, okay.
So this is really just convention. It's just code convention. There's a secret attribute that has what a triple underscore, or a double underscore, but not a double underscore on the other side of it, and that's considered secret. But you basically never use that. And you can still, the point of that was you can still get access to it.
All right. So this is the class we've built to handle all the calculations. Then down below, we have a function you can call that goes through the actual questions on the homework and prints out the answers, after running 50 coin jars for 10 years or something like that. So first off, I'm going to start an IPython terminal and open up a cookie jar class and see what it behaves like. So I have IPython started in the folder that file is, the Python file. And so you see I call from the name of the file, import the objects I want to import. So I'm importing both the cookie jar class and that function, answer homework questions. So now I can say something like, A is a cookie jar with the defaults in here for number of transactions per day and number of days until we consider a year or whatever. So we do that. And so let's run this filler up function. So if we look at that, it basically runs through one instance of the cookie jar set by all of these parameters up here. You see for number of days until full. We're not going to print the summary each week for this one. Or maybe we should. It might be informative. It'll record the day at which we have 500 pennies in our coin jar, right there. And if we want to dump our quarters off to pay for laundry, we can set this variable here so that it does that. So let's see what happens. First off, I'm going to change the print summary of each week to true.
Well, why don't you use the doc string to see what happens and do discover, so you can discover what the keywords are.
There's no summary.
Well, how else you can do it? From within IPython. Set a double question mark.
So the double question mark opens up the text file itself.
Well, no, it gives you access to the code. It shows you the code.
Right, right. So the variable I'm looking for is print summary. Oh. Print summary every week. Didn't need the there we go. So I'm going to run a year's worth of transactions. There it is. I guess it doesn't print the full summary. But let's see what A has in it now. So we're going to run this print A, and it will call that _str function. And so we have $190.98 after 1,800 transactions, and it took us 111 days to reach 500 pennies. So let's actually answer the homework questions using this answer homework questions function here. So the first question is, what is the average total amount of change accumulated each year if you make 5 transactions per day? And what's the 1 sigma scatter about this quantity? So to do that, we build a set of 50 jars. So here we have n jars equals 50, and then we build each of these jars, and then we fill them up. And so now we're going to have this variable jars is a list of filled up cookie jars that have each been simulated for a year. And we'll find the mean of the final values of each of those jars and the standard deviation. And then we'll print it out here, right there. The second question is, what coin are you most likely to accumulate over time? And does it depend on the number of transactions per day? So here, in our class up above, the cookie jar class, the purses are stored as dictionaries, where the keywords are nickels, quarters, etc. And then the number is the number of each object you have in the coin jar. So for the jars we've created up here, we're going to record in our list of firsts which type of coin had the most by looking at these parameters here, and which had the second most. And then we'll print that out. And then we're going to do the same thing for a new set of jars that each have a number of transactions that are different from 5. So here we're going to range from 2 to 20 in steps of 10. Is that right? Yeah. And then we'll record the statistics for each of those at different numbers of transactions per day. And then we'll go to question number C, which is if you remove 8 quarters each week from your purse before dumping it in the coin jar, how many quarters do you have at the end of the year? And so here we have this variable complete quarters, which we built into our coin jar class to handle that for us. So let's just run this function, answer homework questions, and see what statistics we get. All right, so it's printing off the answers as it comes up with them. So in here we have print out the answer to question A. Looks like we accumulate $183 or so over the course of the year, and over 50 trials, there's a scatter of about $5. Here it's running through the different transactions, or number of transactions per day, and trying to see whether that affects the final outcome of which coin is most likely. And you can see for 5 transactions per day, pennies were by far the most likely. In every case, every one of those 50 jars, we had more pennies than anything else. Looks like 43 out of 50 times, we got more quarters for the second most likely coin. Sometimes dimes were the second most likely coin. And see, those basic statistics are pretty much invariant under the number of transactions per day. So we did it for 2, 10, and 20 transactions per day, and pennies are always the most likely. Sometimes quarters are the second most likely, and sometimes dimes. And here, question C, if we remove 8 or as many quarters as we have, less than 8, from our purse each week to pay for laundry before dumping it into coin jar, how many quarters are left after a year? And it's not really that much. In different trials, this is somewhere around 28, 30, something like that. So it's usually right around there. So I hope you guys take the time to look through this and look through how we built the class and then used it to answer statistics about this model we presented. If you have any questions about it, please ask now or ask us later. And this should be up on the website as soon as possible.
Defining every member variable or as like a self dot whatever, it looks like in some places there's lots of self dot da da self dot da da da. And is that useful, or is there any way of just calling that variable without saying self at all? Or?
I think to pass variables, so that's a self dot xxx variable is a property associated with the instance of a class, right? So each instance of a class has some value. So there has to be some way to differentiate between, that instances, properties and an outside variable. So I don't think there's any workaround to that. I've always used self dot whatever.
I mean, so within every method inside of a class, you can have variables that don't have a self component, right? And there you're just using it, and as soon as you leave that method, then all those variables are the same. So the thing that's nice about this is you can call a method, you can operate for whatever you need to do. You can change some of these values. And then when you're done, those still persist as part of the object. I mean, in some sense, that sort of persistence of attributes is the reason why you want to do object-oriented programming, right? Because you can go off, do some computation, go do other things in your code, and then you come back to that instance, and it already knows everything about itself and its prior history.
Yeah, for example, we started that coin jar called A right at the beginning, and since then we've probably built 400 coin jars and destroyed them. But A still has properties, same as before, that are unchanged. So if you really don't want to keep typing the selfs, you could assign an internal variable, the self dot value, and then reassign it after you're done dealing with it, if that makes sense. You could have A equals self dot A at the beginning of the function, and then at the end of it say self dot A equals A. But it seems kludgy. And another point, I saw a few people run into this yesterday. When you call a function or a method, sorry, I keep sort of interspersing those words, but you call a method for a class, you also need that self prefix. So let me find the example. So here, within the method filler_up, it calls the method perform a day's worth of transactions, but you have to identify that as associated with the class. So that's a self dot, blah, blah, blah.
Whenever it doesn't have self dot, it looks outside of the class.
Well, first it looks inside the class for a variable you've named. So, I could say up here, A equals 2, and then further on, if you go to A, it'll look for that. If there isn't a defined variable inside the class that you call, it'll look in namespaces in first. So if I'm inside this method and call variable A, which is not defined in this method, it'll look first inside the class itself to see if, up here, I defined a variable A, and if it's not there, then it will look in the namespace of the, the global namespace, is that the word?
Sorry.
Yeah, no worries. I think that's the word I'm looking for. So it looks through hierarchies until it finds it. And if it goes all the way up to the global namespace and doesn't find it, it spits back an error. It says, this is not known.
So in general, a function will, if it doesn't find a variable name it's calling looking for, it will go to the higher namespace.
Yes. It'll keep stepping up until it hits the end and finds it. So that's one thing you need to be conscious of and both use your advantage and don't get caught by is namespaces in Python. They're very important. And they're built the way they are for reasons. So I can have, for example, I could have a variable called A inside this function, but if then I can also have a variable called A in the global namespace, and those two things are very different because they live in different namespaces. Any other questions? Great. Random chance of costing some dollar amount. And we want to collect statistics over how a coin jar where you dump the remainder from each transaction into, how that changes and accumulates change over a period of time. So we asked you guys to solve this problem using a coin jar. Let's see if I can get this centered better. A class we would call coin jar. So this is the solution that will be up online, or I think actually already is. Where you could figure it out yourself for the context information you needed to solve the problem. So that's why we set it up as sort of a coin jar instead of something that seemed like a real science problem, because we wanted to facilitate the methods as soon as we could without requiring you to learn all the background and nitty-gritty behind the actual science. So we hope that this is a practice that gets you comfortable with some of the techniques of using this object-oriented language. All right, so I'm not going to reread the problem. I'll go over it real quickly, but hopefully you guys looked at the homework. Of course, you make a number of purchases each day. Each purchase has a range. And what we have here is a much more general object than you probably really need to solve just this homework problem, but hopefully it'll be illustrative when we go through some of it. We have our class here, we just started. We have the init function, which you see comes with a double underscore like all of these special functions will. And we have a bunch of default variables up here we've defined, which we'll go over more down below. And here, all our init function does is assigns self variables to these default variables up here, or whatever you choose them to be. All right, day 3, here we are. So I'm going to go ahead and talk over the solution we'll present for the homework problem from last night. Josh wanted to point out that this is, of course, only one way of solving this problem. And the whole point behind this type of homework problem was we wanted to get you guys trying some scientific techniques in a context that you understand. We could have presented a very similar Monte Carlo modeling problem using astronomy data. But then those of you who aren't comfortable using astronomy data would have had to learn all the background behind that, et cetera, et cetera, et cetera. So we wanted to give you a problem where we didn't lay out all of the information you needed, but it was in a context and situation. These aren't important right now. We'll come back to a few of them when they get important. So we have the init function as part of our class. Then we have a set of functions that actually solve our problems for us. So this function here models a set of transactions. So let's go into this one and sort of explore what the actual functions we make this work. The actual functions we use to pull this off look like. So here's one of the problems that you have to solve when doing this homework problem, is how do you determine the best change to return when making a transaction? So I would really advise when you build a class